So my name is Jing Tang. I'm an ecosystem modeler. I work a lot with mathematical models. I'm currently a tenure-track assistant professor at the University of Copenhagen, Department of Biology. Yeah, so we have this vote established last year. So the majority of people are focusing on collecting the data, observation data from different scales, from the microbes, from the soil, from leaf, and also from like lake, oceans. So I came in as a modeler, so I could work closely with the people collecting different measurements data. And then the plan is that we will put some of the observed relationship or the observed patterns into the models and test or use the model to upscale and explore different interactions and assess the impacts. So models are like simplified real world. So they are built on many different mathematical equations and parameters. So they are very useful tools for understand some of interactions, process interactions, but also very useful for explore some scenarios, how the future climate change might influence ecosystems, or how the ecosystems might influence the climate the other way around. So they are useful tools for explore different scenarios compared to do experiments, and also we can systematically explore the interactions. Right now I have a few ongoing projects. One project is a Willow Young Investigator project focusing on understanding the differences between the plant and air temperatures for the Arctic plants, and also want to know what these differences means for plant physiology or the carbon fluxes. And then we want to put this knowledge also into the models to see, after correctly account for plant temperatures, how that will influence the predictions of their greenhouse gases estimations, for instance, in the Arctic. So I have another project which is funded by the department. So it is in supporting the collaborations between the terrestrial ecology and the freshwater biology sections. So in that project, we hired PhD students who will work on coupling lake biogeochemical models into our dynamic ecosystem model, LPG gas. And then since that the lake greenhouse gases has not been accounted in these large-scale models, so we want to know what are the differences after we account for the lake biogeochemical process and also land-lake interactions. So this project will particularly focus on the high latitude regions. So in particular in the Arctic, lakes are very prominent landscape features. Around like 30% of the land areas are covered by the lakes. But currently, like I said, that the models didn't account really the land-lake interactions, how the nutrients or carbon from the land could influence lake greenhouse gas fluxes. But also like in the Arctic, the permafrost is a very important also features that once with the strong climate warming in the Arctic, more permafrost can be thawed and then turning into a lake systems. So all of these features has not been accounted when we talk about the Arctic greenhouse gas budget. So that's why we think that it's important we start to add the lake models into the terrestrial models and then explore these interactions and also update the greenhouse gas budget under the current and the future climate. Yes, so I think that in general my ambitions are still doing what I'm currently doing, but then refine the models, and also try to refine not only the ecosystem models, but also try to better understand the feedbacks, how the ecosystems change the, for instance, atmosphere compositions, and how they change the aerosols, for instance. And also another ambition is that since we have these very good opportunities in the world, so I really want to bring more process understandings of the volatile variations or the fluxes into the models by accounting for, for instance, like lake volatile fluxes or from the microbes, for instance. Thanks for listening.